Welcome to this coding walkthrough. In this session, we'll explore problem number 127, word ladder, a popular problem that tests your understanding of graph traversal techniques. Let's dive into the problem and uncover efficient ways to solve it. In this problem, we are tasked with finding the shortest transformation sequence between two words, a starting word, called begin word, and a target word, called end word. The transformation must follow certain rules. First, you can only change one letter at a time, and second, every intermediate word you create during this transformation must be part of a given dictionary called word list. Importantly, the begin word itself is not considered part of the transformation sequence. If no valid sequence exists that satisfies these conditions, the result should be 0. The input consists of three parts: begin word, the string you start with, end word, the string you aim to reach, and word list, the list of valid words that can be used during the transformation. The output will be an integer, which represents the length of the shortest transformation sequence, or 0 if no sequence is possible. To understand this better, let's look at the first example. Here, the begin word is hit, the end word is cog, and the word list contains the words hot, dog, lot, log, and cog. The shortest transformation sequence is hit-hot-dot-dog-cog. Notice how at each step, only one letter is changed, and every intermediate word exists in the word list. The length of this transformation sequence is 5, which is the output. Now, consider another example where the begin word is still hit and the end word is cog, but this time the word list is slightly different. It contains the words hot, dog, lot, and log, but not cog. In this case, there is no valid transformation sequence because the target word, cog, is not part of the word list. As a result, the output is 0. Finally, let's take a look at a shorter example. Here, the begin word is A, the end word is C, and the word list is A, B, C. In this case, the shortest transformation sequence is A-C. Since only one letter changes and C is part of the word list, this sequence is valid. The length of this sequence is 2, which is the output. These examples highlight how the problem requires us to not only find a valid transformation path but also ensure that the path is as short as possible. Next, let's examine the constraints and edge cases that apply to the problem. The given constraints specify that the length of begin word will be between 1 and 10 characters, and end word will always have the same length as begin word. The word list can contain up to 5,000 words, and all words will consist of lowercase English letters. Additionally, begin word and end word will always differ. All the words in the word list are unique, which eliminates duplicate entries. Edge cases include scenarios where the end word is not in the word list, as seen in example 2, or when the word list contains only one word, which matches the transformation sequence, like in example 3. We also need to consider cases where the transformation requires very few steps, or where the word list is large and has many branching paths. The algorithm must efficiently navigate through these possibilities to find the shortest valid sequence. To start, let's consider the brute force approach to solving the word ladder problem. The basic intuition here is simple. We try generating all possible transformations of the begin word by replacing one letter at a time, and then check if the resulting word exists in the word list. If it does, we proceed recursively, exploring all potential transformation sequences until we eventually find the end word. This method essentially performs a depth-first search, or DFS, across all possible paths. However, there are some important observations to make. First, because this problem is about finding the shortest transformation sequence, an approach like DFS, which explores paths deeply before backtracking, might not be the most effective. A level-order traversal, such as breadth-first search, is better suited for problems involving shortest paths. Second, the large branching factor, where each word can have many valid transformations, makes DFS computationally expensive. The trade-off here is that while a brute force approach is straightforward to implement, it becomes highly inefficient for large inputs due to its exponential time complexity. It also fails to capitalize on the shortest path nature of the problem, which is central to finding an optimal solution. Now, let's move to an optimized approach using breadth-first search, or BFS. The intuition behind BFS is that it's ideal for finding the shortest path in an unweighted graph. In this problem, we can think of words as nodes and valid one-letter transformations as the edges connecting them. Starting with the begin word, we explore all valid one-step transformations in a level order manner. The moment we encounter the N-word, we know we've found the shortest transformation sequence, and we can return its depth as the result. The key steps for implementing this are as follows. First, we initialize a queue, adding the begin word along with its depth in the transformation sequence. We also use a visited set to keep track of processed words, which helps us avoid cycles. For each word at the front of the queue, we generate all possible one-letter transformations by replacing each character from A to Z and checking if the new word exists in the word list. If a transformation matches the end word, we return the current depth. Otherwise, the transformation is added to the queue and marked as visited. If the queue is exhausted without finding the end word, it means no valid transformation sequence exists, and we return 0. The advantage here is clear. BFS ensures that the first time we reach the end word, it's through the shortest path. However, the naive BFS approach can still be slow for large word lists because of the overhead involved in generating and checking all possible transformations. To address the inefficiencies of naive BFS, we can use an optimized BFS with pre-processing. One key observation is that the bottleneck in BFS lies in dynamically generating all valid transformations for each word. Instead, we can pre-process the word list to create a mapping of intermediate states to words. For instance, for the word hot, we generate intermediate states like *OT, H*T, and HO*. These intermediate states represent patterns where one character is replaced by a wildcard, and they map to all words that can be formed by replacing the wildcard with any letter. The pre-processing involves creating a dictionary, often called all_combo_dict, which maps these intermediate states to lists of words. For each word in the word list, we generate all its intermediate states and populate this dictionary. Once the pre-processing is complete, we execute the BFS using this dictionary. Instead of generating transformations dynamically, we directly fetch valid transformations for each word from the all_combo_dict, significantly reducing the computational overhead. This makes the BFS traversal much faster. While the pre-processing step adds some overhead, specifically O and *m², where n is the number of words and m is the word length, it pays off during the actual traversal, making the overall approach more scalable and efficient. The chosen strategy for solving the word ladder problem is the optimized BFS with pre-processing approach. This method strikes a balance between clarity and efficiency by directly addressing the problem's requirements, finding the shortest path in an unweighted graph, while also minimizing redundant computations during traversal. The pre-processing step, though slightly costly, proves invaluable for scaling the solution to larger inputs. Let's break down the complexity. The time complexity is O and *m², for pre-processing the intermediate states, and O and *m, for the BFS traversal, where n is the number of words and m is the word length. The space complexity is O and *m², for storing the all_combo_dict. Alternatives like the brute force approach are infeasible due to their exponential complexity, and even naive BFS struggles with redundant transformation checks on larger inputs. By leveraging pre-processing to streamline the search process, this strategy ensures correctness, efficiency, and scalability, making it the optimal solution to the word ladder problem. Let's continue. Let's continue. Let's continue. Let's continue. Let's continue. Let's continue. Here, we begin by importing the necessary modules, dec for our queue operations and defaultdict for handling the adjacency list of word patterns. Inside the ladder length function, we first convert the word list into a set, called wordSet, to enable O1 lookup times. This ensures our algorithm performs efficiently when checking if a word exists in the list. If the end word is not present in the word set, we return 0 immediately, as it's impossible to transform the begin word into an end word that's not in the list. Next, we pre-process the words to create a pattern_map, which groups words by their intermediate patterns. For example, replacing one character in a word with an asterisk creates a pattern like H*T for the word hot. This pattern becomes a key in the map, and all words matching that pattern are stored in a list as its value. This pre-processing step is crucial for efficiently finding neighbors during the transformation process. After this setup, we initialize a breadth-first search, BFS, using a queue. The queue stores tuples containing the current word and the transformation length, starting with the begin word and a length of 1. We also initialize a visited set to avoid revisiting words, which helps prevent infinite loops during BFS traversal. The BFS loop continues as long as there are items in the queue. For each word dequeued, we generate all possible patterns by replacing each character in the word with an asterisk, just as we did during pre-processing. For each generated pattern, we retrieve its neighbors from the pattern underscore map. If one of these neighbors matches the end word, we immediately return the current transformation length plus 1, as we've found the shortest path. If a neighbor isn't the end word and hasn't been visited yet, we mark it as visited and add it to the queue with an increment transformation length. To optimize further, we clear the list of neighbors for the current pattern in the pattern underscore map after processing it. This prevents redundant checks for the same pattern in subsequent iterations. Finally, if the queue is exhausted without finding the end word, we return 0, indicating there is no valid transformation sequence. Here, we begin by importing the necessary Java utilities and defining our solution class. The main method, ladderLength, takes 3 parameters: the starting word, the target end word, and a list of words that can be used in the transformations. We first convert the word list into a hash set for efficient lookup, and we immediately check if the end word exists in the set. If it doesn't, we can return 0 right away because no transformation sequence is possible. Next, we pre-process the word list to create a pattern map. This map will store all possible intermediate patterns for each word. For example, if a word is hot, we generate patterns like *ot, h*t, and ho*, by replacing each character with an asterisk one at a time. These patterns are then used as keys in the map, with the corresponding words as values. This pre-processing allows us to quickly find neighboring words that differ by just one character during the BFS traversal. Finally, the BFS setup begins. We initialize a queue to store pairs containing the current word and the transformation length, starting with the begin word and a length of 1. A visited set is also initialized to keep track of words that have already been processed, ensuring we don't revisit them and create infinite loops. Now, the BFS algorithm processes the queue. For each word dequeued, we extract its transformation length and then generate all possible patterns for the current word by replacing one character at a time with an asterisk. These patterns allow us to retrieve the neighboring words from the pattern map. For each neighbor, we first check if it matches the end word. If it does, we found the shortest transformation sequence, so we return the length increment by 1. If the neighbor hasn't been visited yet, we mark it as visited and add it to the queue with an updated transformation length. This ensures we only process each word once, avoiding redundant computations. After processing all neighbors for a pattern, we clear the associated list in the pattern map to prevent unnecessary rechecks of the same pattern later in the traversal. This optimization reduces redundant checks and helps the algorithm run more efficiently. If the queue becomes empty and the end word hasn't been reached, we return 0, indicating that no valid transformation sequence exists between the begin word and the end word. To support the BFS implementation, we define a simple helper class called pair. This class is generic, meaning it can store 2 related values of any type. In our case, it represents a pair of the current word and its associated transformation length. It has 2 fields, key and value, which are initialized through the constructor. Getter methods, getKey and getValue, are provided to retrieve these fields. By using this pair class, we can neatly package the word and its transformation length together, making the BFS queue more intuitive and organized. This concludes the implementation, where the BFS algorithm effectively leverages the pre-computed pattern map to find the shortest transformation sequence, or determines that no such sequence exists if the end word is unreachable. In this example, we are tasked with transforming the word hit into cog using the given word list. The first step is pre-processing. We start by converting the word list into a set for faster lookups, resulting in word set containing hot, dog, lot, log, and cog. Next, we check if the target word, cog, exists in the set. Since it does, we proceed. To optimize our search, we create a pattern map where each word is broken down into its intermediate forms by replacing one letter at a time with a wildcard. For instance, hot generates the patterns *ot, h*t, and ho*. We repeat this for all the words in the list, creating a map of patterns to their corresponding words. This pre-processing step sets the stage for efficiently finding connections between words in the next phase. Finally, we initialize a queue for the BFS algorithm with the starting word hit and its initial transformation length of 1. We also maintain a visited set to avoid revisiting words, starting with hit. Now, we begin the BFS execution. The first word we process is hit, with a transformation length of 1. The patterns for hit are *hit, h*t, and high*. Matching h*t with the word list, we find hot. Adding hot to the queue and marking it as visited, the queue becomes deek, hot, 2. Next, we process hot, which has a length of 2. Its patterns are *ot, h*t, and ho*. Matching *ot, we find dot and lot. Adding these to the queue and updating the visited set, the queue becomes deek, 3, lot, 3. Moving on to dot, with a length of 3, its patterns are *ot, d*t, and do*. Matching do*, we find dog. Adding dog to the queue, we now have deek, lot, 3, dog, 4, and an updated visited set. From dog, with a length of 4, its patterns are *og, d*g, and do*. Matching *og, we find log and cog. Adding these to the queue results in deek, log, 5, cog, 5. Finally, we process cog, which matches the target word with a transformation length of 5. At this point, we return 5 as the shortest transformation sequence length. The output for this example is 5, representing the shortest sequence of transformations from hit to cog. Now, let's look at another scenario where no path exists. In this case, the input consists of the same starting and ending words, hit and cog, but the word list only includes hot, and dog. During preprocessing, we convert the word list into a set, resulting in word set containing hot, and dog. Checking for the presence of cog in this set, we find that it is missing. Since the target word doesn't exist in the list, we immediately return 0, as no transformation sequence can be completed. In this final example, we are given a simpler scenario where we need to transform the word it into C using the word list, B, C. After converting the word list into a set, we have word set containing a, B, and C. Checking if C exists in the set, we confirm that it does, so we proceed. The pattern map for this case is straightforward, as each word generates the same pattern, *. With BFS, we start with the initial word and a transformation length of 1. The pattern * matches B and C from the word list. Adding these to the queue gives deek, B, 2, C, 2, and the visited set becomes a, B, C. Processing C, we find that it matches the target word, and the transformation length is 2. Therefore, the output for this example is 2. To analyze the time complexity of the word ladder problem, we break it into two primary components, preprocessing and BFS traversal. First, during preprocessing, we convert the word list into a set for faster lookups. This step takes k*n time, where n is the number of words in the list, and k is the average length of each word. Next, we generate the pattern _ map, which involves iterating over each word in the set and creating patterns by replacing one character at a time. Since each word has k characters and generates k patterns, this entire process takes k²*n time. Now, for the BFS traversal, in the worst case, we process all valid words reachable from the begin word. Each word generates k patterns, and matching these patterns to their neighbors is 1, due to the adjacency list. The BFS traversal, therefore, takes k*n operations for all words. Additionally, clearing pattern lists to avoid redundant checks also takes k*n, as each pattern is cleared only once. Combining these, the overall time complexity involves k²*n for preprocessing and k*n for BFS traversal, giving us a final total time complexity of k²*n. Now, let's focus on the space complexity of the word ladder problem. The first major contributor is the word set, which requires n space to store all n words from the word list. Then, we have the pattern _ map, where each word generates k patterns, and each pattern stores a list of words matching that pattern. In the worst case, this requires k*n space. For the BFS traversal, we use a queue to store intermediate states. At most, the queue contains all n words, requiring n space. Similarly, the visited set tracks all visited words, which also requires n space. Among these, the dominant term is the space required for the pattern underscore map, which is k*n. Therefore, when we combine these contributions, the overall space complexity of the solution is k*n. Let's compare the optimized approach to a brute force solution. In a naive brute force method, we would check all possible transformations of the begin word by iterating over the entire word list. For each word, comparing character by character takes k time, and repeating this for all n words across all transformation levels leads to exponential time complexity, n*k² per transformation level. Over multiple levels, this results in an overall complexity of n to the power of l*k², where L is the length of the transformation chain. The optimized solution, however, preprocesses patterns to avoid redundant checks, reducing the complexity to k²*n, which is significantly faster, especially for larger inputs. Now, considering best, average, and worst case scenarios, the best case occurs when the n word is directly reachable from the begin word in the first BFS level. Here, the time complexity is k²*n for preprocessing and k for BFS. In the average case, preprocessing dominates with k²*n, and BFS traversal adds k*n. Finally, in the worst case, all words are processed, requiring k²*n, preprocessing and k*n, BFS traversal. The quadratic dependence on k arises from generating k patterns per word, while the linear dependence on n stems from processing all words. This optimized solution ensures shortest path guarantees and is far more efficient than the brute force approach. One common issue when solving the word ladder problem is not accounting for word length mismatches. Some solutions assume that all words in the word list have the same length as the begin word, but this isn't always guaranteed. Failing to validate this can lead to incorrect transformations or even runtime errors. Another common mistake is revisiting already processed words. If you don't mark words as visited, your BFS or DFS might revisit them, which could cause infinite loops or unnecessary calculations. To avoid this, always use a visited set to track words you've already processed. Next, inefficient transformation checks can also be a problem. If you naively iterate through the entire word list to find valid transformations, the complexity can grow to n*m per word, where n is the size of the word list and m is the length of each word. A better approach is preprocessing the word list to group words by intermediate transformations, like replacing one letter with an asterisk, to make lookups faster. Lastly, there are edge cases you should never overlook, such as when the begin word isn't part of the word list, when the list is empty, or when no valid chain exists. Handling these explicitly helps avoid unexpected behavior. And for optimization, consider using bidirectional BFS. Unlike single-direction BFS, it reduces the search space by meeting in the middle, making it much faster for this type of problem. Now, when you're in an interview, there are a few key insights to keep in mind. First, make sure you can explain why BFS is preferred over DFS for this problem. BFS is ideal for shortest path problems because it guarantees that the first valid path it finds is the shortest. Also, interviewers often look for candidates who optimize the search space. Preprocessing the word list into a dictionary of intermediate states, like mapping h*t to words such as hot and hit, demonstrates that you're thinking about efficiency. Don't forget to proactively discuss edge cases too, like an empty word list or scenarios where no transformation exists. This shows you're thorough and prepared. If time allows, you can also compare different approaches like brute force, BFS, DFS, and bidirectional BFS. Talk about their trade-offs in terms of time complexity, space usage, and implementation difficulty. Lastly, it can be helpful to mention related problems. For instance, LeetCode 126, Word Ladder 2, builds on this problem by requiring all shortest transformation sequences. LeetCode 433, Minimum Genetic Mutation, and LeetCode 752, Open the Lock, are other BFS-based problems with similar concepts, so studying those can deepen your understanding of transformation-based algorithms. Finally, let's explore some alternative approaches and their trade-offs. The brute force approach involves generating all possible transformations for each word and checking if they exist in the word list. While this method is simple to implement, it's highly inefficient, with a time complexity of n*m, where n is the number of words and m is the word length. It also has minimal space overhead, but the poor performance makes it impractical for larger inputs. A more efficient option is BFS with preprocessing. By preprocessing the word list into a dictionary of intermediate states, you can optimize lookups and reduce the overall complexity to n*m. However, this does require additional memory to store the preprocessing dictionary. Another advanced approach is bidirectional BFS, which starts from both the begin word and end word, meeting in the middle to minimize the search space. This method is faster than single-direction BFS, with the same n*m complexity, but it's more challenging to implement due to the need to synchronize the two searches. Each of these approaches has its strengths and weaknesses, so the best choice depends on the specific constraints and requirements of the problem you're solving. Great job following along. To recap, we used BFS to solve the word ladder problem efficiently by focusing on the shortest path in an unweighted graph. Remember to practice similar problems and refine your graph traversal skills. Thanks for watching, and stay tuned for more coding sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!